Previously, we've looked at what's called the average or differential rate. And that's that one where you have rate equals negative 1 over A, delta A over delta T, etc. So you're relating it to every reactant and product. And in order to calculate the rate, you need to watch as the concentration changes over time. And so it gives you a relationship between rate and time. What's the rate between 5 and 10 seconds, between 10 and 20 seconds? This is useful sometimes, but it's not always what we're interested in. Sometimes we just want to check, okay, what would the rate be initially if we put in this much of my reactants? So we might want to be shooting for a particular rate. So instead of having some data and just figuring out what the rate is, what we might want to do is figure out, well, what would I have to do to make the rate become a particular thing if I put in this much of each reactant? And so we want a relationship between just the rate and the concentration. What would the rate initially be? We know that the rate's going to change over time, but at least when I first put in that concentration, what would my rate be? And maybe we're shooting for one in particular. So in this case, we can write what's called a rate law, where for a really simple reaction like this, A plus B go to products, wherever they are, the rate law looks like this. Rate is equal to K. K is called the rate constant. It's just a constant of proportionality that gives you an idea of how fast your reaction is. Big K means fast, small k means slow. The exponents, X and Y, are called the reaction orders with respect to the whatever reactant they're on. And if you add those together, they give you the overall order. Now, we can't figure this out just by looking at this reaction equation. We actually have to do an experiment, but we'll talk about that in a different video. For now, let's just look at how we could write a rate law given some information and what types of calculations we could do with that. So, for instance, let's look at this question here. The following reaction is first order in NO3 and second order in NO2. And it tells me the rate constant is 0.053 molar to the negative 2, second to the negative 1. First thing, write the rate equation. Really easy. So we know it's going to have this general form. Rate equals K, and then A to the X, B to the Y. So now we just need to fill in the information that we have. So we know rate equals K here is my rate constant. So I'm going to plug that in, 0.053 m to the negative 2, s to the negative 1. I just write that in. A here, my first reactant molecule would be NO3. And it tells me that it's first order in NO3. So that just has an exponent of 1. My second reactant is NO2. And it tells me that's second order. And so I'm just going to put a 2 there. Really simple. So that's the rate equation or the rate law for this reaction. The overall order, we just need to add up these two numbers here, 1 plus 2. So the overall order is going to be 3. So now we have the rate law for this reaction, and it's third order overall. We can also do some really simple calculations. So I've just rewritten this now, make my life easy, nice and legible. We have our rate law. By what factor does the rate change if NO2 is doubled and NO3 held constant? So we say, okay, if, this is a constant, our rate constant, of course, and NO3 is a constant, but I doubled my concentration of NO2, how would that affect my rate? This is the type of question someone in industry might ask. And what we can do is we can sort of say, okay, well, I have rate equals, and, my K is not going to change, so I'll just write K, and my NO3 is not going to change. Oops, NO3. So I can leave that there. But let's say I doubled NO2. So whatever NO2 was, I did 2 times NO2. And now I want to pull this number out. Well, I have a 2 here, and I see that it's squared. So 2 squared gives me 4. So I'm going to have 4 times my K, and then my NO3, and then my NO2 squared. So we can see this is just what my rate looks like. I just wrote out K because I was being lazy, didn't feel like writing out the number there. And now, since I doubled this, I see that my rate has increased by a factor of 4. So all I have to do is plug in my number here and then do the math and see what number comes out in front. If I had tripled my rate, I would put or tripled my NO2, I would put a 3 here, and so on. So my rate's going to increase by a factor of 4 if I double NO2. Okay, so that's more of a conceptual type one, but what about just doing some math? Calculate the rate of the reaction with these concentrations. Super easy, exactly what you would think. I just plug it in. 0.053, m to the negative 2, s to the negative 1. My NO3 is 0.055 molar, and my NO2 is 0.115 molar, and I can't forget that it is squared. So first of all, we can look at our units and say, okay, well, I'm going to have 3 m's total here, right? M times m squared. And I have m to the negative 2 here. So if I sort of do up here, m to the negative 2 times m cubed. So we're going to add our exponents together, and we're going to end up with m to the first. So we always want to make sure we track our units. Math part's really easy. I just do this, times this, times this squared in my calculator, which I'll do right now. All right, and I get a really tiny number, and that's all right. Rates are usually really small. So I get 3.8 times 10 to the negative 5. Ooh, it's a little hard to read. That's at times 10 to the negative 5. So I get a pretty small rate. My m's leave me m to the first, and I still have this second to the negative 1. So I calculate the rate. It's 3.8 times 10 to the 5 molar per second with these particular concentrations. So any concentrations they gave me, I would just plug into my overall rate equation, and I can calculate my rate.